Okay, so here's lesson 11, number 3. So what I said is whenever we see a switch, we'll know that this is a transient problem. Transient problem where I'm going from one steady state to steady state, right? What we'll call initial steady state and final steady state. And along the way is what the transient equation is, right? So you can even think of movement, right? I'm transient when I'm walking from Bancroft to Rickover, right? I'm moving along the way, and then I'm in a steady state once I'm in Bancroft, or I'm in a steady state when I'm in Rickover. But as I'm moving, and then this E is moving in our equation. E is just the exponential on your calculator, E minus T tau. And that's the rate at which we're moving. So the three things that we're solving for is going to be the initial steady state, and this is a capacitor. Right here's the C capacitor, which means we're going to be solving for this voltage, which they've already labeled for us right there. Right? See, it says V sub C. So we're solving for the voltage. So on this equation sheet, when I'm looking at capacitors, there's the equation. I'm solving for three things. Here's the first thing I'm solving for. Here's the second thing I'm solving for. And then tau is the third thing I'm solving for. Right? V final, that's the same number 1. And tau right here is made up of R and C. Well, C is a given, right? It's right there on the thing, but the R that we need to solve for, right, there's C, 60 microfarads, that is C. And so the R that we're solving for is going to have to be R Thevenin, right? Tau is made up of R Thevenin and the C that's given. Tau is the T, in case you're confused. Every time I keep saying it's a Greek symbol, kind of looks like T, tau. So I'm solving for R Thevenin, and the reason why is because that's the resistance as seen by the capacitor, which is how we do Thevenin, right? We treated something as a load. Well, in this case, we're treating the capacitor as the load that's looking back at the circuit. I need one R to plug in, and so it's R. It's not R1 plus R2. It's not some equivalent resistance looking from the source. It's the Thevenin resistance looking back at the thing. So what this is saying says the circuit below does not have the same charge and equation since the voltage drop is controlled by the voltage divider rule. So what this is telling, it doesn't actually say, it should say it's been open for a long time. It should say open for a long time. Open for a long time. In fact, I think I need to email that to everyone, that number 3, lesson 11, number 3 has been open for a long time. Therefore, the initial equals 0. There, I sent that to the rest of the groups. So this V initial, because it's been open for a long time, V initial is 0. Does that make sense? That it is not plugged in to a voltage source, right? Whenever it's open, the circuit essentially looks like this. Right? There is no voltage source. So all the charge that was inside of this dissipated into that resistor until it finally reached 0. So if it's been open for a long time, then its V initial is 0. Anybody have not comfortable with that idea? Nope. Okay. So then what we're going to look at now is whenever it is plugged in, right, this is closed. And as soon as it closed, it starts charging, right? Inside of this capacitor, it starts charging. And so what we're going to do is we're going to take this equation. It says write the charging equation. I mean, if you're going to get points for just writing the equation, if I know I have a capacitor in transient, then I could just rewrite this formula right here, this, and I'll get points just for writing that formula. And now we're plugging in essentially each of these parts. So right here, V sub C, which is the voltage across the capacitor as a function of time, is equal to that V final plus V initial minus V final. E negative T over tau. And what we're going to do is we're just going to solve for each of these parts. Well, we already know V initial equals 0 volts. Check, got that one. So now let's find V final. And the reason we're going to do this is so that we get the R Thevenin, but the E Thevenin essentially will also be that V final. So if I do it, transform it into a Thevenin, right here, there's R1, there's R2, and then I remove the load, right? And that's how we find V Thevenin or E Thevenin, same thing, E Thevenin, V Thevenin, but it's the voltage across these open nodes, which in this case is the same as the voltage, right? There's the nodes. It's the same as the voltage across the 20 kilo ohm. So now I'll use voltage divider rule, and I'll say that the voltage being shared amongst these series elements, right, 2 and 20 are in series with each other. 44 volts is being shared. I'm looking across the 20 kilo ohm resistor, and the two that are in series is 22, right? So this is 20 over, oh wait, I made a mistake there. I should be over 22. There we go. 2 plus 20 makes 22. Sorry if that confused you. So now I have the voltage divider rule, and I'm looking across this open. Well, now this is 40 volts, and that is my E Thevenin. It's also the voltage across the fully charged capacitor, because what does a fully charged capacitor look like? An open. So once if I'm solving, it's the same step as solving for E Thevenin. When I solve for the E Thevenin, that is like V final. So I could go ahead and plug this in. 40 volts plus V initial, 0, minus 40 volts. E to the negative T over, oh, we have one more thing to solve for, which is tau. We got to find the time constant. Well, the time constant, we said was RC. Well, the R that I need is that R Thevenin. So how do I solve for R Thevenin? I remove the load again. So this was my E Thevenin circuit, right? Here's my E Thevenin circuit. On the right over here, I'll draw my R Thevenin circuit. Right, I remove the load, or in this case, I remove the capacitor. I have a resistor, and then I zero the source for R Thevenin. Zero the source for R Thevenin. What does 0 voltage look like? Miles. Is it a short or an open? 0 voltage.
Open.
So 0 voltage would be the short, 0 current would be the open. That's how I actually remember it. I say like 0 current. 0 current is an open. Because like I can imagine, even as we've done these circuit simulators, is that whenever I have a current that I remove something out of it, nothing flows through it. So it's 0 current. Whereas 0 voltage is a short, which you can also think of as just putting in a wire, right? So now I have this wire that I've replaced that voltage source with for my R Thevenin. I'm looking back from here. So I have a node here, I have a node here, and what I see is they both share the same 2 nodes on the outside, right? So my R Thevenin is equal to 2 paralleled with 22. And what that comes out to is 1.82 kilo ohms. So in this case, I have 1.82 kilo ohms. That's that R Thevenin. The capacitance is 60 microfarads.
Sir, I'm kind of confused as to how you see that 22 as
On my R Thevenin?
yeah, how is that parallel?
Yep. So looking right here, whenever I place it with a wire, maybe I drew too many lines, but right here is a wire. And so the current, we'll put the current in green. We said that we're looking for R Thevenin from here. And remember, whenever we're looking for resistance is measured in ohms. So it's like using an ohm meter. And what it does is it's looking by sending a small amount of current. So the current comes up through here and it splits like that.
Okay. Yes, sir.
And then once they each hit that node, right? Say that you messed it up and you didn't label that node in orange. You label it like this. Well, it's been split up, and then they both rejoin when they hit the orange down there.
Okay.
Does that make sense?
Yes, sir. Thank you.
So then they come back together, and it takes it from point A to point B. That's really what we're looking at. What is the total resistance from A to B?
Okay.
So now, right, the charging equation. So we're looking for tau. We plug each of these together. And I get 109. Actually, I should type that on my calculator. You can't read this handwriting. I think it's 109 microseconds. 1.82 E3 times 60 E negative 6. Nope, that's milli. Glad I checked it. So it's 109.8 milliseconds. So that's the thing that I plug in down below, that 109.8. 109.8 milliseconds. How long will it take for it to fully charge? Well, we said full charge is 5 tau. 5 tau. So 5 times 109.8 milliseconds, and that is 549 milliseconds. So there's my equation. If I wanted to simplify it one more time, I could by saying, and this is just the math, I'm leaving the 40, I'm leaving the 0 out. And so it's like saying 40 volts minus 40 e to the negative t over 109.8. And then I simplify by pulling each of the 40s out. But if you get it to this right here, I'll call this good. You should remove the 0 from your equation just because you don't leave a 0 in there. You could leave it like this, but another way to write it is 40 volts. And this is just 1, right? I pulled 40 volts out, I pull the 40 volts out, and I get 1 minus e to the negative t over 109.8 milliseconds.
Sir, will there ever be an exception to the 5 tau rule?
Nope, it's a truth about just how e to the negative t over something works. You could just go plug that in right now. And so say that, that's a good question. And I'll show real quick. So right here, if I had e to the negative t over tau and say that t was equal to, 1 tau. Well, now it's just tau. That's like saying e to the negative 1. So if I had 2 tau, e to the negative 2, because the taus are what's canceling out. E to the negative 5, I just type it on my calculator and it'll say e to the negative 5 gives me 99, or let me say this another way. Right here, 1 minus e to that. 1 minus e to the 5 gives me 99.3%. And so it always is true. 1 minus e to the whatever gives me 99.3. So it gets me 99.3% of the way there. And in truth, the reason why that was is because back in the day, whenever they had, imagine like a little panel, an instrument panel with little ticks along it, think of like your gas gauge. And so back whenever they could look at these things with like a voltmeter and you could look at the voltage across it, well, whenever after 5 tau, if it got down to here, you can't visually see past that. Does that make sense? So
Sure.
that's the history on where the 5 tau became the rule of thumb. But it gets you 99.3% of the way there.
Thank you, sir.
Yep. All right, y'all want to go to the breakout rooms or see the inductor one?